Hello guys, welcome to part 4 of Rocket Science 101. It's been a while, but I'm back. Yeah, it's kind of a busy semester this year, so we'll see how it goes. I really can't make any promises as to how frequently I'll be able to upload these, but today we'll be working on part 4 is going to give us some chemistry and thermodynamics background. Chemistry. Okay. Alright, so the reason we're doing this is, let's take a peek at this book. Open it up to the table of contents. What we're going to be doing pretty soon here, chapter 3 covers nozzle theory and thermodynamic relations. So I thought we'd cover a lot of thermo today, and so we'll be prepared for that. Okay, so let's get started on some chemistry stuff. First, let's define what is a chemical reaction. A chemical reaction. It's a process that transforms an initial set of chemicals into a new set of chemicals. So basically, it takes reactants and turns them into products. So, a chemical equation is usually how we will depict a chemical reaction, and it's just a symbolic representation. So I'll just give an example here. So this here would be iron oxide and aluminum combining or changing and giving iron and aluminum oxide. Now, why did I put numbers in front of these? Well, stay tuned. And I'm not sure, but I think this is like thermite or something. I don't know. I don't remember what this reaction is. It's just an example. And there are so many different kinds of reactions. Just some that I can think of right now, types of reactions. We've got, well, acid-base. Yeah, my memory card just got filled up there. Sorry about that. So we have acid-base, which it either, well, it'll combine an acid and a base and turn it into a salt, basically, so to speak. Also we have oxidation and reduction, also known as Redox. Whatever, that's good for now. There are other kinds. Anyway, I want to talk about the latter one that I mentioned, oxidation and reduction. Because this is basically the type of reaction that occurs inside of a rocket engine, a chemical rocket engine. So, what happens in this kind of reaction? Well, what we have is two kinds of reactants. We have oxidizers and we have reducers. Basically, the oxidizer will take electrons from the reducers. I think that's right, yeah. Actually, a way to remember this, it's kind of a fun mnemonic. Leo the lion says Grr. And this basically means that if it loses an electron, it has been oxidized. And if it gains an electron, it has been reduced. So let's give an example of a redox reaction. We'll have a few hydrogen atoms combine with oxygen, and we'll get two water molecules. So what happens here? The oxidizer is oxygen. I don't think that's where the word oxidizer comes from, because it's spelled different. Oxygen is oxygen, not that's a Y, not an I. But anyway, it is the oxidizer though. So basically, it takes the electron from the hydrogen, and then they combine and in a covalent bond for water, or hydrogen bond, whatever. I'm actually not a chemist. I'm just pretending. I'm playing one on TV. So yeah, this transfer of electrons is actually what releases energy. That's where the energy in the combustion chamber actually comes from. Anyway, let's move on and start talking about stoichiometry. So what is stoichiometry? Well, conservation principles tell us that matter can neither be created nor destroyed. So the amount of matter you have on the reactant side of a chemical equation has got to be equal to the amount of matter you have on the products side. And so basically all of the let's say hydrogen atoms on one side, if you count them all up, they have to equal the number of hydrogen atoms on the other side, and that goes for all of the atoms involved. Now they can change form, of course, because that's what's going on in our equation. The only exception to this would be if we have like a nuclear reaction and we're taking uranium and shrinking it down to whatever it turns into. I don't remember, but then that's the only case where that rule doesn't really apply, because actually we're converting mass into energy, and then we're getting into E equals mc squared and all that. And, well, let's forget I said that. Anyway, so basically conservation of mass. And now to illustrate this, say we have CH4, I think that's methane, plus oxygen, and this turns into carbon dioxide and water. So look at this. Alright, we've got one carbon on this side and one carbon on this side, so that's fine. We've got 4 hydrogens on this side, and oh, we only have 2. What's with this? Okay, so the first thing we have to do is balance this equation. We have to come up with coefficients in front of each of these that will lead to everything being balanced. So we're good on the carbon, but I'm going to hold off on putting 1s there for now because you never know. So look, we have 4 hydrogen and 2 hydrogen. So in order to make this 4 and 4, I'll put a 2 there. Let's go ahead and put 1s here. So we have one carbon, 4 hydrogen, 2 oxygen, and 2 4 oxygen. So let's make this 4 oxygen. Now we're balanced. Now, what is stoichiometry? Well, it's basically the ratio of these coefficients in a reaction. So a stoichiometric ratio, is the ratio of one reactant to another, or product. If you want to know how many water molecules will result from how many oxygen molecules in this reaction, so like that would be 2 H2O per 2 oxygen, or we could have 1 methane per 1 carbon dioxide, or 2 water, or whatever, you know, stuff like that. And this will be useful when we're trying to calculate how much of this do we need to use up all of this. So we'll use an example here. Actually, before I get into this example, there's just one last concept I need to talk about, and that would be the quantity known as the mole, also known as just mole, like that. It's basically a quantity of atoms or molecules that allows us to know how much mass is in 1 mole. So how much 1 mole of such and such weighs. It's called the molar mass. But how many atoms is a mole of atoms? 1 mole equals 6 point... Oh my gosh, it's been a while. I think it's 2.6. Oh dear, I'm getting a little nervous now. Times 10 to the minus... so molar mass is basically how much does 1 mole of blank weigh. And basically you can get that from the periodic table, which, darn it, I don't have one accessible to me at the moment, do I? Looking. Where's the periodic table? Oh, darn it. One sec. I found it. Yeah, this is what I used in my chemistry class. I don't want to write on here in pen, but anyway, this number below the symbol, so let's take oxygen for example, that's the molar mass, and it's in grams. So I don't know if you can see that there. Let's zoom in. Whoa. Alright, let's look at copper, Cu. Don't ask me what's Cu. I think it's Latin, like cupric or something. But below the symbol is the mass in grams. This one is 63.5 blah blah blah. Okay, so now that you know what a molar mass is, let's launch into our example. So, a rocket carries liquid oxygen and liquid hydrogen, let's say, and combines them to form water. So we have our reaction here that we were looking at before, 2H2 plus O2. Okay, so we have our reaction that we were talking about before with hydrogen and oxygen, and they combine to form water. Alright, now let's say that we know how much mass of water we're going to get when we fire our rocket. Let's say we know that we'll get mass of the H2O equals 800 kilograms. And let's figure out how much mass of each of our reactants we need to get that. So MH2 is what? And M of O2 is what? Let's see. I guess that's everything we need to get started. So we're going to do some, what do you call it? Dimensional analysis, or, no, we're going to, what is it called? Anyway, unit conversion stuff. Basically, used a lot in chemistry. So we start with the quantity we know, 800 kilograms of H2O, and first what we got to do is convert it to grams because our molar mass is in grams. So we know that we have 1,000 grams per kilogram. Now what do we got to do? Let's convert it to moles. So we'll have 1 mole on top. Oh, and if you don't know what I'm doing, you multiply it like this because kilograms will cancel, and now we have grams, the unit we want. Okay, so now we want grams to cancel, so what's the molar mass of water? Well, if you don't know, I actually know, but look it up on here. A water is an H2O, so we have 2H, which is 1.01 or so, and we have oxygen, 1 oxygen, which is 16. So 1.01 times 2 is 2.02 plus 16 is 18.02 grams. So now we have this in moles. If you calculate this out, we get, I don't know if you can see that, but 800 times 1,000 divided by 18.02. And that's 44,400 or so moles of H2O. Now, at this point, we take this equation and we go 2 directions. We go and use our molar mass, our stoichiometric ratio for hydrogen and for oxygen. So let's do hydrogen first. We multiply this by 2 moles of H2O for every 2 moles of H2, so really nothing happens, but I'll show it anyway. 2H2O per 2H2, and then convert it to grams again. I won't show it, but it's 1.01 on our periodic table. Grams of actually it's 2.02, isn't it? Grams of H2 for every mole of H2. And then we convert it to a mass, which is I meant to say it's already a mass. I meant to say convert it back to kilograms because we were given it in kilograms. So we take what we had before, we multiply it by 2 and divide by 2, so I won't do anything. But then we multiply by 2.02 and divide by 1,000, and we get 89.7 kilograms. Alright, same thing for oxygen. So in this case we have one oxygen for every 2 hydrogen. And then convert that into a mass by using the molar mass. What's the molar mass of molecular oxygen? It's 16 times 2, which is 32. 32 grams of oxygen for every mole. And then convert it to kilograms and divide by 1,000 grams. And we get 44,400 or so, divided by 2 times 32 divided by 1,000. And we get 710.4 kilograms of oxygen. You will notice that when you add these two up, so that answer plus 89.7, and we get about 800. It's not exactly 800, of course, because we had some rounding errors, but so that just goes to illustrate that mass is conserved. 800 kilograms of of products comes from 800 kilograms of reactants. So there was just a nice little example. I was going to have us convert it into volume so we can know how big to make the fuel tanks, but I didn't want to look up the density for hydrogen and oxygen. Anyway, that's all I have for the chemistry. In a moment we'll move on to thermodynamics.